Hey everyone, thank you so much for showing up and hanging around. For me, this is going to be a very interesting talk. I currently do a lot of stuff with solar energy, and the rare earth metals are an integral part of that industry, both in battery storage and in photovoltaic cells and all. So this is going to be a good talk. Phil is a geologist, mineral dealer, and collector living in the west side of Denver. His passion for geology and mineral collecting began as a child living near the fluorescent mineral capital of the world, Franklin, New Jersey, and then eventually led to a BA in geology from the University of Colorado at Boulder in 2012, and a master's degree in economic geology with a focus on geochemistry and petrography at the Colorado School of Mines in 2017. He's been a co-author and collaborator on numerous scientific papers, abstracts, and magazine articles on mineralogy and geology with a focus on rare earth element minerals. Pegmatites of Colorado. He enjoys public speaking and has given dozens of talks for mineral clubs and events, as well as helped organize several scientific symposia in Colorado. He's been involved in mineral dealing and collecting community for close to 20 years. How can he be? You're only like 22.
35, and give me a little credit.
Okay. And is currently employed full-time as a mineral dealer in Denver, Colorado. So if you would all please welcome Phil.
Well, thank you guys. Thank you, first of all, for coming. Looks like the sound just kicked in. Hopefully everybody can hear me okay. And yeah, thanks for being here. It's good to be at another Denver German Mineral Show. So I'm going to apologize because I didn't know I was going to be projecting off a big screen TV. So some of these slides may be a little bit hard to read. Hopefully we'll explain the text in such a way that you won't need to read everything that's on there. So today we're going to talk about rare earth element minerals in Colorado. And rare earth elements are something that I'm sure some of you are familiar with, maybe some of you not so much. Hopefully this talk will get you a little more familiar with rare earth elements and the diversity of interesting rare earth element deposits that we have here in Colorado. So all of you know that Colorado is really a wealth of rare and beautiful minerals. These are just a handful of the minerals from the state. Colorado has an incredible diversity of crystallized and non-crystallized mineral specimens from many different environments. These are some of the minerals that we're probably familiar with from Colorado. Obviously our rare rhodochrosite, smoky quartz and amazonite, topaz and fluorite and things like this. These are some of the minerals that maybe we're not so familiar with from the state of Colorado. And you might be looking at some of these photographs and thinking, so what, they're all ugly. Well, this is why they're important. Just taking one example, the Pikes Peak Batholith, we have what I would really call a world-class example of a so-called niobium, yttrium, fluorine, NYF type pegmatite district. And this has over 80 species and 30 large pegmatites that have a whole host of interesting, unusual minerals and unusual elements. And rare earth elements are used, as our introducer was alluding to, in a lot of different technologies that are important right now. Renewable energy systems, mobile electronics, computers, and a lot of other technologies. So therefore, understanding why and how these rare earth elements fractionate to form these deposits is really important for looking at our future sources of these elements and things that we call these so-called critical elements in different technologies. So before we go into the minerals and the geology, I just want to give a little bit of an overview of rare earth elements and what they are and kind of how they occur in geologic environments. So rare earth elements are a row of the periodic table, sometimes called the lanthanide row, and they're characterized as having very high charges, so typically +4 to +6, and they all have a high what we call Z/R ratio. So that means that they have a high ionic potential, and cation repulsion leads to less stable solids. So essentially what you want to take away from that in a geologic setting is that they tend to behave in what we call an incompatible way. So when I say incompatible, what I mean is igneous rocks, for example, are crystallizing from magmas and lavas and things. They prefer to stay in the liquid form versus going into solids or minerals. And because of that incompatible behavior, the rare earth elements often occur in rocks that we call highly fractionated rocks. So these are rocks that have undergone a really protracted crystallization and we'll go into a little bit more detail on that. This diagram up here is a little bit busy, but the main thing to take away from this is that very often our rare earth element deposits occur in what we call extensional environments. So these are environments where the crust is thinning, there's extension going on. We have that happening in the western US right now, in the Great Basin, but we also have that happening in Colorado at different geologic periods. And we think that some of our rare earth and rich deposits here in Colorado have to do with these extensional tectonic terrains. And when you do that, when you thin the crust, you allow mantle melting to happen and mantle-derived material, mantle-derived magma to ascend, and that tends to be more rare earth enriched, and that leads to a whole process of fractionation and enrichment where you get these elements concentrating. So we're going to start with the Pikes Peak Batholith, and I imagine pretty much all of you here are familiar with the Pikes Peak Batholith to some degree. It's probably our most famous rock formation here in the state for mineral specimens. It is about a billion-year-old pluton. It's got a big surface expression area, about 3,800 square kilometers. It's composed primarily of biotite and hornblende, cyanogranite to montagranite, and the important thing for our rare earths is that it's really a classic example of what we call an A-type granite, and this is a granite that's not associated with a mountain building or tectonic episode. It's actually associated more with the extension that we just talked about, and that's going to be important when we start to talk about rare earth concentration. It's intruding mainly 1.7 billion-year-old metasediments, the Idaho Springs group, and also important for our rare earth discussion, it includes a bunch of late-stage plutons and dikes, and these can be divided into two populations. One of them is more sodic in composition, and the other one is more potassic. So just a quick overview showing the location here of the Pikes Peak Batholith in North America and some of our tectonic setting back in the Precambrian. You can see that we're kind of in the central part of the country here, obviously, and we're in what's called the Yavapai Mazatlan province. And that is part of the story when we look at the extension that we think happened in the crust that led to the formation of the batholith and the upwelling of these magmas that would later form the Pikes Peak Batholith. So a little more zoomed in view here of the batholith. You can see we're just kind of south of Denver here and a little bit to the west between Denver and Colorado Springs. And you can see here on the geologic map on the left, most of that red there, that's coarse grained granite. The pinkish and the other colored blobs, let's see if my pointer's working here. Oh, this is like the weakest pointer ever. Anyways, these other colored blobs here, these are our late stage rocks. These are our sodic and potassic plutons. And most of you have heard of Lake George, where the fabulous amazonite that Mark was talking about comes from. That is one of our late stage potassic plutons. And down in the south, we have Mount Rosa, which is more of a sodic late stage pluton. So we're going to zoom in a little bit here on some of the pegmatites that have our interesting rare earth deposits. We're going to talk specifically about the South Platte Pegmatite district. This is up here in the north in orange, and that contains about 100 significant matte pegmatites, and these are large zone bodies that don't have a clear relationship to the late stage plutons, but they have a lot of interesting rare earth minerals, and these are similar geologically to places like the Llano Uplift in Texas or the Ytterby Pegmatites over in Sweden. We also have a lot of neolithic type pegmatites, which usually are a little less rare earth enriched, but they have euhedral crystals of amazonite, topaz, fluorite, etc., and sometimes actually produce very nice crystals of our rare earth minerals, which normally don't occur as euhedral crystals. Down in the south, we have Mount Rosa, which is a late stage sodic pluton, and it's a little bit different geochemically. It's got a riebeckite granite and some pegmatites that are a little bit different that we'll talk about here in a minute. So zooming in here a little bit on the South Platte Pegmatite district, you can see again our view of the overall batholith that we just looked at. And you can see here kind of in the upper right, a zoomed in view showing some of these pegmatites. Generally, these pegmatites are divided into two sort of subtypes, so to speak, based on rare earth content. One is our kind of alunite monazite subtype, which is going to be more light rare earth enriched. And then our other type is the euxenite eudolinite subtype, which is going to be more heavy rare earth enriched. And this is a part of a classification system that was devised by Peter Cherney and others in terms of subdividing these NYF pegmatites into sort of different families based on geochemistry. So another quick overview of the South Platte pegmatites before we go into kind of a case study example here. They tend to have this wonderful zonation, and this photo here is actually showing a pegmatite, the Oregon number 2 pegmatite, where you can see this quartz core standing out there in the middle because the intermediate zone, which is composed of microcline, was what was actually being mined. That was mined for feldspars, for ceramics primarily, and that quartz core was left standing there in the middle. And this zonation process is a product of crystallization, and I won't really go into that in detail, that it's going to be important for our rare earth story here. So I thought I'd focus on one pegmatite in a little bit of detail here in the South Platte, and that's a pegmatite that we call the Wellington Lake pegmatite. And this is a recent study that I was involved in. This locality was known to mineral collectors for a number of years. It was known colloquially as the Cave of Wonders because it really is like a cave. You can see there's an opening there into basically a big, single, large, mirrolitic top-style pocket. And it really is quite different than a lot of the other South Platte pegmatites in that it has this giant single pocket. So just zooming into where Wellington Lake is there, you can see our previous map. We're kind of on the northwest margin there of the batholith. This is where the Wellington Lake pegmatite is. And the pegmatite, like I just said, is characterized by large open pockets. So this is obviously quite hematite stained and kind of dirty looking in this photo, but these are actually giant quartz crystals on the left. We have some botryoidal hematite, and then if we zoom in down in the corner there where that kind of inset is, we can see that there are some kind of brown lumpy things that are basically floating in this clay here in the central part of this pocket. And these turned out to actually be fluorocerite bastnäsite crystals, which actually got up to about 3 centimeters. And when we clean those off, they actually look pretty nice. They look like this. And this is actually one that is sliced in half here for analysis. And you can see that these crystals have a beautiful zonation. The core is bastnäsite, which is a rare earth carbonate. And then the rim is actually fluorocerite. And you can see some quantitative chemical data here. We actually did some microprobe analysis on these. And not only did we do microprobe, but we did some TEM work using a tunneling electron microscope, and we found that this is actually an epitaxial overgrowth on the bastnäsite, which is interesting. So here's a little bit of chemical mapping that we did on the fluorocerite bastnäsite over at the Colorado School of Mines. We used an instrument called a ChemScan, which is quantitative evaluation of minerals by SEM, kind of a mouthful. That basically what it allowed us to do is to actually map the distribution of rare earth elements within these crystals. And we saw some really interesting patterns as far as fractionation of these elements. And we also saw nicely on the left there the boundary between the fluorocerite and the bastnäsite. We also did some electron microprobe analysis of these crystals. And again, you can see that boundary there between the two minerals. And we saw some interesting trends here that we actually graphed here at the bottom as far as variation in rare earth elements as you go across this boundary. And something I want you to kind of think about a little bit as I go through this talk is the idea of fractionation at different scales, right? So we talked about the Pikes Peak Batholith as a whole being fractionated. We talked about the pegmatite being fractionated, but we also see this fractionation happening at a single crystal scale. And this is something really interesting to think about when we want to understand why are these rare earth elements behaving in nature the way they do, and how can we apply that to potentially finding deposits of these elements. So another pegmatite I'll talk about in a little bit of detail here is the white cloud pegmatite, and this is another one that we studied in the South Platte District fairly recently. It's kind of in the same area. You can see on the right here, zoomed in a little bit, the white cloud pegmatite is kind of on the eastern end of the South Platte District there. And it's a really interesting pegmatite. It has a real diversity of rare earth species, and you can see kind of a view of part of the pegmatite core right there in that upper photo. So the white cloud pegmatite is really one of the most mineralogically complex pegmatites in the South Platte District. It has a lot of different rare earth minerals. It's a zoned pegmatite, measures about 300 by 125 feet, and it's zoned in the way that we just talked about. There's a quartz core, and then there's sort of a quartz microcline zone, an intermediary zone. And then there are irregular zones that are up to about 15 by 20 feet that are dominated by fluorite. And in those fluorite-rich zones is where most of our rare earth element minerals are. And you'll see this very commonly in deposits around the world, an association between fluorite and rare earth element minerals. And I'll talk a little bit more about that in a minute here. So rare earth minerals of the white cloud pegmatite, there's quite a few interesting ones. This slide is actually a little old. That says fluorothalonite. We actually did some analysis on this and turned out that all thalanite has fluorine, so now it's just thalanite. But thalanite is an interesting mineral. It's actually a heavy rare earth enriched mineral, and it's one of the very few minerals in nature that actually has like weight percentage quantities of elements like lutetium and ytterbium. Usually you'd see these minerals in ppm levels, so it's really interesting to have a mineral that actually has large concentrations of these unusual heavy rare earth elements in it. We also have cinchosite, which is a light rare earth element mineral. We have fergusonite, occurring as nice crystals. Canosite, actually, this was a one-time find, was found as very nice unusual crystals. And there's some gadolinite that's typically massive as well. Another view of the outcrop here in the quarry, showing some of the thalanite and fluorite there, that kind of interesting texture, and you can see some of the purple fluorite. So not the prettiest stuff in the world if you're used to euhedral crystals, but a very mineralogically interesting assemblage. So again, a little bit of imaging and data that we did. We looked at the gadolinite specifically, and we tried to understand rare earth zoning in the gadolinite. And we saw some interesting stuff. We saw zoning that actually was controlled by crystallography planes, which we sort of expect as the crystal is growing. It incorporates elements into it differently. But we also saw some domains that were actually cross-cutting across the crystallographic boundaries, and we interpreted some of those as maybe being a hydrothermal overprint, which is interesting because you don't typically think of rare earth elements as being influenced by hydrothermal stuff. So a little more data. I know this is very hard to read here, guys, so I'm not going to go into this too much, but we also looked at the thalanite specifically, and we saw some of the same trends as far as rare earth fractionation and zoning. We saw some overprinting in terms of elemental abundance, or what we interpreted as overprinting that we think might be hydrothermal, which is interesting. And we also did some graphing of the rare earth content. These charts are called spider diagrams, and it's a way of graphically expressing the rare earth abundance, or rare earth distribution, I should say, of different rocks and minerals to try to get an idea of kind of how they compare to each other. So one more pegmatite I'll talk about in the South Platte is the Oregon No. 3 pegmatite. This is a really interesting pegmatite. It's quite large. You can see it's a big open cut quarry, and again, they were primarily mining the feldspar, but also some of the quartz core. And then behind it is Raleigh Peak, which is kind of a landmark in the area. And specifically, we're going to zoom in on these two areas that are circled there in the pegmatite, because this is where about 9 years ago I found some very nice specimens of samarskite, which is a heavy rare earth mineral. It's an oxide that contains quite a bit of uranium as well, so it's fairly radioactive. But we actually found some very nice specimens up to about 10, 12 centimeters that show some nice crystal forms, some kind of plumose crystal form going on. And those were collected up here, so in a sort of albite replacement zone. And this is very typical for these rare earth pegmatites in the South Platte, that the rare earth minerals either occur with fluorite or they occur in these albite zones where you basically have fine-grained, sugary albite, and then the rare earth minerals are in this kind of late-stage albite zone. And this was collected, by the way, with a scintillometer. So the way that I located this was with a Geiger counter, and I could tell that it was radioactive. I found the spot, I started digging, and then I found a bunch of these specimens. Here are some specimens from the Luster No. 1 pegmatite that are at Harvard. These were collected by Mark Jacobson, I believe, who's right here, and gifted to the Harvard Museum from the Luster Quarry, which is next door. That's now, unfortunately, the site of somebody's house, so you can't go there anymore. That produced some very nice samarskites as well. The Little Patsy pegmatite is another one that's quite interesting. It's in the same area, and it's a fairly large pegmatite. You can see a scale here. It's several hundred feet wide, and it shows very nice zonation. And this pegmatite was actually one of the last to be mined in the district. It was actually mined on and off up until the early 1980s, and has been fairly productive as far as mineral specimens. So probably the most interesting thing from the Little Patsy pegmatite is fluorocerite. Fluorocerite is a rare earth fluoride, so it's basically a light rare earth fluoride, and it can occur in wonderful crystals at the Little Patsy pegmatite. This is really one of the few places in the world where you get macroscopic crystals of this species. And on the left there is my hand holding a very nice crystal group. On the right are two excellent specimens collected by Rudy Bologna, who's a very accomplished field collector of rare earth minerals in Colorado, and really produced some wonderful examples of this mineral Basically, all of these came from a very small zone in the pegmatite, and at this point, it's still possible to find these, but it's become a little more difficult. Some more interesting rare earth minerals from the little Patsy pegmatite. Another thing that you can collect there are these specimens of thorite that's associated with Pggmatite. So thorite is obviously a thorium mineral and it's quite radioactive, so again, the best way to find these is with the Geiger counter. But these are interesting because they actually occur between these giant biotite blades. So you basically have these huge biotite books in the outer zone of the pegmatite. These can get up to about this big. And in between the biotite crystals are where you find these Pggmatite and also sertolite zircon crystals. Sertolite is basically a metamixed variety of zircon. It's got uranium and thorium in it and also rare earth elements. A little bit more of the South Platte, or Little Patsy rare earth minerals. This was one particularly good collecting trip I had there. You can see my back table there is covered in fluorocerite crystals and little Pggmatite and thorite specimens as well. So definitely had some good productive trips to this locality. The Oregon number 2 is in the same area. That's actually the pegmatite, next to the pegmatite rather, that I showed in the first photo with the nice zoning. This pegmatite is interesting because it has a little bit of a different rare earth mineral assemblage. Particularly, it's known for these large specimens, and you can see a beer can for scale there, so those are pretty big. These are giant chunks of bastnasite, which has actually replaced alunite. And it's pretty interesting to think about how a rare earth silicate, which is what alunite is, can be replaced by a carbonate. That's kind of unusual geochemically to have that happen. That this was a particular find that I made in the winter of 2014, and I found some huge specimens of this material. And to my knowledge, this is the only place in Colorado where this really occurs, at least at this scale. So this was kind of interesting. A few more rare earth minerals from the South Platte District. I'm obviously not going to talk about every one of these localities. Xenotime actually occurs as very nice crystals at the Big Bertha pegmatite. There's about a 1-inch xenotime crystal there. Samarskite's been found at the Black Cloud pegmatite, as well as a number of others. Some nice crystals there. On the right, I know that's hard to see, that photo, but that is a fantastic specimen of crystallized bastnasite that's about 6 centimeters wide. Again, with an overgrowth of fluorocerite, and this is probably the best example for both species in the United States. This was found in a single merolytic pocket in Wigwam Creek, that's in the Dave Bunt collection. And if you want to see that specimen, it's actually on display over in the DGMS room, so go check out that specimen. It's really truly a remarkable thing for Colorado. And it was found by itself in a merolytic pocket, so I know we have some accomplished diggers in the audience. When you guys are digging, don't throw away the little brown rocks. Make sure you look for them, and if in doubt, show them to me, because they may be something really unusual, and often they're fairly nondescript. And sometimes you can have a pocket of Amazonite or aqua or whatever, and you just have one of these crystals for whatever reason, and that's it. So we're going to move a little bit to the south now, out of the South Platte, and talk about the Mount Rosa Granite. This is where I did my master's thesis of mines. And this is a really interesting area. It's quite different than the rest of the Pikes Peak Batholith in that it's more sodic in nature. It's dominated by the Mount Rosa Granite, which is a rhyolite granite. And there's a whole cluster of pegmatites surrounding the Mount Rosa Granite that are chemically quite different than the other Pikes Peak Batholith pegmatites. So again, I'm not going to go over all this, but the main thing to take away here is that it's the southernmost of these late-stage plutons in the batholith. It's probably also the youngest, and it includes a whole interesting diversity of rock types ranging from phthalite-bearing granite to sodic amphibole granite to diabase dikes. There's all kinds of weird stuff, and there's also quite a few pegmatites. So here's a typical Mount Rosa pegmatite. You can see this nice contact here by my hammer. And you can see these big crystals of rhyolite, which is a sodic amphibole, that are actually perpendicular to that contact. And in the core of that pegmatite, we actually have some cryolite, which is interesting as well. Here's a little schematic that I did for my master's thesis, trying to understand how these pegmatites form. The main thing to take away from this is that we have an inward progressing crystallization sequence, right? That the pegmatite intrudes, and then you have that melt, that pegmatite melt is cooling, and you have crystallization going inward, but not only do you have magmatic crystallization, you actually have hydrothermal fluids forming as well, and that's where a lot of our rare earths are associated. and that's where a lot of our fluorine and other unusual minerals are as well. So one interesting thing that I found down in the Mount Rosa area are these pyrochlore crystals. This one on the right was not collected by me, that's an older piece in my friend REE's collection. But the one on the left was actually collected by me, and that's actually a fairly large euhedral crystal of pyrochlore, and this is about the only place in the state where you actually get nice euhedral crystals of pyrochlore. And pyrochlore contains rare earths. It's not, I don't believe it's rare earth essential, so to speak, but it usually does have some rare earths in it. This little specimen is actually a microcline crystal with little bacillite crystals on it. This is in the Harvard collection that was probably collected by Ed Ober back in the 1940s or 50s. This is an interesting mineral. This is actually only known from St. Peter's Dome, Carbonatite. This is a really complex mineral. I've never collected this one, but I'm sure it's out there somewhere. And it just gives you an idea of the crazy chemical complexity of some of these minerals. Some of these rare earth minerals people call garbage can minerals because they really tend to incorporate all kinds of elements that other minerals don't want, so to speak. A few nice bacillite crystals from Stowe Mountain. These were actually purchased by Harvard in 1932 from Ed Ober, which is pretty interesting. And a few other things from the Stowe Mountain, St. Peter's Dome area. These are from an excellent Rocks and Minerals article by Gary Zeno and Sarah Hansen, showing some very nice bacillite crystals there on the upper right, some nice euhedral zircon crystals that are actually on microclines, and then we have some nice sharp zircon crystals down there. And also some rare species that occur as micros. So most of the places I've collected these minerals in Colorado, these occur as macroscopic specimens. But some of these places like St. Peter's Dome and Stowe Mountain that produce pockets, these actually occur as very nice micros as well, for those of you that are into micromounting. So here's a few images from my master's thesis. These are BSE images, which is backscatter electron, for those of you that aren't familiar with it. And basically these are very high power images taken of different mineral assemblages. And what this allows us to do is identify a lot of these unusual phases, unusual minerals, and actually do some analysis and also understand how they're associated. And the thing to take away from this slide is that not only do we see these minerals in a primary sense, so actually crystallizing from a melt or a fluid, but we also see a lot of interesting pseudomorphs and replacement going on. So what you're seeing here is actually minerals like the rebecite and the strophyllite that are actually being replaced by rare earth carbonates and rare earth bearing fluorite, which is pretty interesting to think about. So we're going to move back up north now, out of the Pikes Peak Batholith, and talk about the Rusty Gold Prospect. This is an interesting locality that's been known since the 1930s or so, and it's basically west of Boulder. This geologic map, I know it's a little bit hard to read, but basically Boulder would be just off the map to the right there in the middle, and there's Jamestown, and we are in what's called the Longs Peak St. Vrain Batholith, and that is a big granite batholith. It's about 1.7 billion years old, or 1.4 billion years old, I'm sorry, and that is the host rock for our rare earth deposits at the Rusty Gold. So at the Rusty Gold, rare earth mineralization is dominated by these kind of blob-like pods, and they're really interesting looking. You can see a field photo here of this kind of white pegmatite rock with these black blobs in it. And these blobs have a very interesting zonation because they actually have a rim of alunite. The black stuff there, that kind of pencil outline looking stuff, is alunite, and that is completely surrounding these pods. And then what we did is we analyzed these pods, and we found a really interesting distribution of rare earth content. So we found that their overall rare earth content actually increases from the rim going inward to the core of these blobs about tenfold in the heavy rare earth elements compared to light rare earth elements. So again, getting back to our idea about fractionation, we don't have all the answers for this yet, and I think this is something we're just starting to explore in the research world, in a sense. That, why is that happening? Our idea was that basically a rare earth rich fluid that had a lot of fluorine in it either intruded along with the main Longs Peak St. Vrain Pluton, or maybe came in a little bit later and it sort of concentrated rare earths as it crystallized, and that's how we explain some of these patterns is basically an extreme fractionation process happening at a few different scales. So here's a little bit of data from the study that we did on the Rusty Gold Prospect. Again, this is taken using an electron microprobe where we're actually mapping element distribution. And you know, the main thing to take away here is that we have this whole interesting, funky assemblage of these different rare earth elements. We have alunite, we have monazite, we have bastnäsite, we have torn and bomite, which is a weird one that was first found in Sweden. We have cerite. All these are occurring together, and they have a really interesting distribution. If anybody's interested in some of these papers that I'm referencing, I can give you a link. These are all available as PDFs for free online on my friend's website, and you're welcome to go and check them out and download them. So we're going to kind of get a little bit away from the Pegmatites here, and we're going to talk about Carbonatites here as our last example. So some of you probably know what a Carbonatite is, some of you don't. Essentially, a Carbonatite is an igneous calcite, and that sounds like a contradiction. That essentially what you have to imagine is that you have a mantle-derived melt, so a melt that's coming from way down deep in the earth, and that melt contains a lot of volatiles, and specific things like carbon dioxide and fluorine and other things that help it in terms of segregating itself and separating from the surrounding melt and the surrounding rock. But also as this fractionates, right, as our rock is crystallizing and a residual melt is forming, that melt becomes more and more enriched in CO2 and other things, and eventually what you end up with is actually an igneous calcite, so a carbonate melt where you're actually not forming calcite sedimentary, which is normal for calcite, you're actually forming calcite in the igneous process. And the Powderhorn complex, which is down in the Gunnison area, central Colorado, is probably the best example of this in the United States, actually. And you can see that little kind of cone-shaped hill there, that's actually looking at Iron Mountain, which is kind of the central part of this complex down in Gunnison. So here's a little bit of a geologic map of the Powderhorn Carbonatite. So the Powderhorn Carbonatite is Cambrian in age, it's about 500, 520 MA, I believe. And essentially, the idea is that the crust in what's now Colorado was thinning, it was extending, and that crustal thinning allowed some of this upwelling to happen in the upper mantle, and some of this melting and fractionation process that basically emplaced this Carbonatite. And typically in these Carbonatites, we don't just have the Carbonatite itself, we actually have a whole series of rocks that are kind of forming a bullseye pattern around it. And in this case, what you can see here in the middle is this blue, that's the Carbonatite, that's our calcite-dominated rock. And then around that, we have a bunch of other units. We have a peroxenite, which is a very mafic rock that has a lot of titanium in it. We have Pggmatite, which is a weird sodic rock, kind of a nepheline cyanide derivative, you could say. And then we have iolite, which is another weird sodic rock, and we have a few other things. So this whole complex is basically the same age, and it's thought to have formed through the same kind of fractionation and crystallization process. And there's an interesting quote here from a publication saying that the complex of Iron Hill is probably the best example of Carbonatite alkalic rock association in the United States, and is one of the outstanding occurrences in the world. So we're lucky to have that here in the state. So basically, there's two major rock units in the Iron Hill complex that appear to have significant mineral resource potential. One is our Carbonatite stock, and the other is the peroxenite unit. And the peroxenite unit is the first and the most mafic phase of the complex, and that's where we have a lot of not only rare earths, but we have quite a bit of titanium. And you can see here in this slide, this was actually drilled back in the 70s and was estimated to have about 350 million tons of titanium reserves, so a big titanium resource. Our other potential resource is the rare earth resource, and that's actually in the Carbonatite. And there was a study in the 70s, and this is actually from a USGS publication more recently, that this is actually potentially a significant resource of rare earths and niobium. So for those of you who might be wondering, well, where are we actually going to mine these rare earths in Colorado? If we actually do this anywhere, and there's still a lot of hurdles to do this, this would probably be the place. And just to wake you guys back up again, if you fell asleep, here's a couple of beautiful topaz crystals from the Pikes Peak Batholith. Had to throw this in there. These are also at the Harvard collection when I was there a few years ago. One last slide. Those of you who are field collectors that might be wondering, how do I go out and find these rare earth mineral localities? A couple different tips. Be there first, obviously. That's true of any mineral locality. Being there early helps. Doing your homework, obviously. Getting online, digging through the literature. Buying a good scintillator is an important thing. This is my buddy Rudy here. He's a very accomplished rare earth collector in Colorado. And there's my friend Marcus, who's my usual field collecting partner. And He's got a scintillator, he's hanging on a rope there, he's got his smart physicist brain that helps too sometimes. So, the really nice thing about rare earth mineral collecting, in my opinion, is that you don't have that much competition. There's not that many people doing it, and you can go out and you can find something cool for a lot less digging than probably a lot of you are used to who dig pockets. So that's it, and thanks for your attention, and if you have any questions, I'll take them. Yeah.
What's your favorite rare earth mineral that you've personally collected?
That is a good question. Yeah, you know, it might actually be the pyrochlore from down at this St. Peter's Dome area. I found about 20 good crystals. One in particular was just awesome. And you know, it's a black mineral. It's ugly to most people, but it's a very unusual mineral to find in the state. I found a single crystal that was about that big. You know, this was back in my grad school days, so I had bills and tuition to pay. I think I sold it on eBay for a couple $100. That's one of the few times that Dave Bunk has given me a hard time about, you know, not selling a mineral to him. So I knew it was good then. So, you know, that's one of the many that kind of got away. Yeah.
So you mentioned fluorocerite and bastnasite?
Yep.
Do either of those have any like uses that we know of, or is it just like minerals?
Yeah, so good question. So bastnasite actually is a pretty significant ore of rare earths. In fact, it's one of the main ore minerals for rare earth elements. So it actually is pretty important. You know, usually at the ore deposits like carbonatites, it's there, but it occurs as tiny little grains instead of crystals. The fluorocerite's pretty rare, so that's more of a collector thing. But the bastnasite actually is a pretty significant ore of the rare earths.
Cool.
Yep.
What is allanite?
Allanite is a silicate, so allanite is actually in the epidote group, so it's actually sort of a relative of epidote, but it has usually light rare earth elements in it. And that can form pretty nice crystals too.
It can be like gem quality?
I don't know about gem quality. I can't honestly, I can think of hardly any of the rare earth minerals that are gem quality. Yeah, that's true actually. Yeah, Rudy's correct. There's a few localities where they occur as gem crystals, but usually not. Yep.
You said you were able to find some really good cathedral examples, and I think you said they were in the little Patsy type.
Yep.
And that was that fluorocerite?
That's the fluorocerite primarily. There's some other minerals from there too. The little Patsy now is actually owned by a guy who's built a cabin on the property. I've actually become friends with him. He's a nice guy. He's given me access there. So that site is potentially accessible, but you need to get access through him at this point. That's true of a lot of the South Platte Pegmatites. Some of them, like the White Cloud, you can go to. Others, you either have to get permission or be willing to be a little stealthy. So, but you didn't hear that from me. Yeah.
How does the igneous formed calcite differ from the sedimentary calcite?
You know, that is a good question. To be honest, I don't know if I'm the best person to answer that. Chemically, they're pretty similar. In terms of chemistry, I think there are some differences, trace element content specifically. But you know, it's still calcite. It's calcite primarily, and the carbonatite, and then you have a fair bit of iron and magnesium as well. So that's going to form stuff like siderite and anchorite and different iron carbonate minerals. Yep.
So you said when you're prospecting out here, you want to use the scintillator. I mean, what kind of numbers are we talking? Are we talking ppm? Are we talking ppb?
No, this can be weight percent levels. I mean, in some of these minerals, this is weight percent uranium and thorium. And having a decent scintillometer or Geiger counter really helps. I mean, some people can do this visually. You know, Rudy is really good at finding these minerals visually. I'm okay at that, but I prefer to use a combination of my eyes and then the scintillometer. The scintillometer is nice because when you're in a dump, let's say, and there's a feldspar that all looks the same and everything's dirty, you can really hone in on an interesting specimen, 2 feet under the surface that you just might not see otherwise. You never find it with a counter. And then when you get close, and this is also true of outcrops, maybe there's a crystal that's hidden behind a foot of feldspar. And you know that it's there because the counter is really elevated. And then you start kind of digging, into that feldspar to try to get it out. So.
Are any of these real hot though?
They can be pretty hot, yeah. Some of them, especially like the euxenite and smarskite and stuff like that, that can actually be quite hot. So, yeah, whereas other ones like the, fluorocerite, that's pretty like nominal radioactivity. Awesome, well, thank you. Oh, one more.
One.
Yeah.
When you find fluorite in a mineralitic cavity
Yeah.
in an igneous rock, is it like is it typical that it would have rare earths in it? Like, is
So
it maybe?
it really depends on the environment, you know. I would say maybe there's a higher likelihood. You know, the fluorite can also have some rare earth content itself, especially some of the greenish fluorites in these granites actually have yttrium in them. You know, we're not talking a ton of yttrium, but it's nice to give it a nice, it's enough to give it a nice green color. And, you know, if you're in a pocket, and I'd say, you know, I mean, you already know this, but it's really worth trying to save everything. It's, you know, don't overlook the small things, don't overlook the micros, because in some of these granite pegmatite environments, you really never know what you're going to find. Sometimes you can really just have one crystal of something special, and that's it.
Is there a
Yeah,
market
right.
for this, for rare earths?
Yes, I mean in two ways. So there's a specimen market. I will say, somebody who actually kind of put myself through grad school selling these minerals. It's a niche market, that there is a market. And certainly as far as rare earths as a resource, this is a big global market. And all the money that the USGS and other organizations are putting into this research, this is to try to develop a domestic supply of these elements. So. Awesome, well thank you guys. Appreciate it.
Very good. Okay, the moral of the story is if you don't know what the rock is, don't put it in your pockets.